are 2 cups of room temperature water. One will be heated up and the other one will be put into a refrigerator. The water in the left cup will be gone, turning into water vapor, while the water on the right will be freezed into an ice cube. If we label the water in the cups, the systems, and elsewhere the surroundings, heat entering the system on the left, making it an endothermic process, while heat existing from the system on the right, making it an exothermic process. Water molecules are known as H2O as it is getting heated up. It turns from ice to water vapor, which is from solid to liquid to gas form. Microscale-wise, the water molecules are speeding up, going from an organized shape to be moving more freely.
All the scenarios we talked about, they're all included under one term, thermodynamics.
Thermal energy, heat transfer. Heat transfer can be referred as Q, and so we come across this mathematical equation Q equals mc delta T, which in this case is the multiplication of mass of the object, its specific heat capacity, and temperature change. In this metal boiling lab, we will be testing the equation by using the equation. We drop a piece of unknown hot metal into a cup of water. The temperature increases as the metal cools down, releasing heat into the water. And before we get into the calculations, the thermometer reads as the temperature increasing, but the metal was getting cooled down. So which object's temperature is this thermometer measuring? The water was touching the metal piece, water was also touching the cup. So what's the relationship of the cup and the metal's temperatures? This will refer to the 0th law of the thermodynamics, thermal equilibrium. This means that the temperature of these 3 objects are the same, reaching thermal equilibrium. With the understanding of thermal equilibrium, we can know that Q surrounding plus Q system equals 0, so therefore Q surrounding equals negative Q system. So in this case of metal boiling lab, Q water plus Q metal equals 0. So we can set up an equation with both sides equal, with Q water equals negative Q metal. With this equation established, we can simply plug in the data, unfoil it, and to get the specific heat capacity of the unknown metal, and we see that it matches with the specific heat capacity of copper, so we know that this metal is copper. Moving on to our second lab, the water heating lab. In this lab, we put our immersion heater in a cup of ice, using electricity to add heat to the ice till it melts and boils, reaching the boiling point. During the melting process, temperature of H2O were noted every 5 seconds for 600 seconds in total. We observed that as time goes on, temperature increases while H2O changes from solid to liquid and to gas, experiencing physical changes. So what is the relationship between these 2 variables? We set time as independent variable and temperature as the dependent variable, and we plot the data. So we plot the data points and wait, it's not a straight line. They're not linearly related. Maybe I plot it wrong, so we replot it. And it's still like that. There are the steep fragments and the flat parts of the graph. H2O was in the forms of ice, water, or vapor as temperature increased, but when it was melting or boiling, the temperature did not change at all. And this leads us to the big conclusion that temperature changes and phase changes don't happen at the same time. There's that big or in the middle. When experiencing a phase change, the mathematical computation of heat transfer is Q equals MLF or Q equals MLV. They are latent heat. MLF is used when vaporizing and condensing, while MLV is used when melting and freezing. Moving on to our last lab, calorimetry. Calorimetry is a calculation of calories in an object by transforming it to a thermal energy and calculating its released heat into the surroundings. In this case, we'll be heating up water using fuels such as methanol. We set up a beaker of water above the flame. Heat gets transferred into the water. This is an exothermic process to the fuel. By keeping track of the water temperature and the fuel usage, we can know the amount of heat produced. For example, that we are heating up water by burning methanol. This is an exothermic reaction because Q reactant is smaller than Q products. But how many heat were getting generated? Well, we come across the term enthalpy. Enthalpy, also known as delta H, is the measurement of energy and the calculations of thermal energy required or released in a chemical reaction. It can be calculated by Q product minus Q reactant. In this chemical reaction, bonds were firstly broken apart in order to reform afterwards. This breaking apart required energy, which came from the flame of the lighter. Atoms then reorganize themselves to form new bonds, which are the products. Forming bonds will then release heat. Partial of the newly released heat will go back to support the next round of reaction. Reactions will continue until no reactants are left. Round after rounds, we gain more energy than we started with. Lastly, entropy. Entropy delta S is the stabilities of a substance. When it's stable, it is low in potential energy, less likely to react with other substances, and is negative delta S. One example can be condensation. When unstable substance is high in potential energy, making it more likely to react with. This has a positive delta S. One example for this is melting. Quick review of enthalpy delta H. Negative is exothermic and positive is endothermic. And with enthalpy and entropy, we can calculate delta G, which determines the spontaneity of a chemical reaction. Equations for spontaneity: delta G equals delta H minus temperature times delta S. And so we have this graph of spontaneity. In the first quadrant, reactions are spontaneous above certain temperatures. In the second quadrant, reactions always take place. In the third quadrant, reactions are spontaneous below certain temperature. And in the fourth quadrant, nothing happens. Finally, I would like to present to you the ultimate thermodynamics chart. Thanks for watching.